Hello everyone, welcome to the lecture again. In the last class, we look at the concept of virtual displacement, virtual work and principle of virtual work. Today, we are going to solve many examples so that we can get familiar with these concepts. Let us look at the first question statement. So, question number 1 and the problem statement is following. Each of the two uniform hinged bars has a mass m and a length L and is supported and loaded as shown. For a given force P, determine the angle theta for equilibrium. Now, before we start this question, first let us follow some sign convention that we will use for the principle of virtual work. So, this is the direction convention. The force direction I am going to take always positive. So, if the force is acting in the x direction, then that x will be positive. And if the virtual displacement is in the direction of the force, then work is also positive. So, with this let us understand the problem. So, here what is happening is you have these two bars and of course, they have a mass m. Because of the mass m, they have a tendency to get close, and because of the force P, we are balancing this tendency of the bar, so that they remains in the equilibrium. And in the question statement, it has asked to determine the angle theta, so that P balance the collapse of these bars. First of all, let me put the directions here. So, I have taken plus x because the P is acting in that direction, and I am taking this direction as positive y because the mass of these rods are acting downwards. Okay. So, let me draw the figure again. So, we have a pin support here and we have a roller support here. This is subjected to a force P, and then the bar are like that. They have a length of L, and in between they makes a angle of theta. Now, the mass of these bars are going to act at a distance of L by 2 and it will be downwards. So, let us say this is mg and that is also mg. Because of the P, the bars are going to go far. So, let us draw a virtual displacement. Okay. This is the effect of P, and note that this is consistent with the constraint, okay, because we have taken the displacement along this surface. Okay. And what will happen because of the weight? So, as I said, because of the weight, it have a tendency to do a motion like this. But note that everything is in equilibrium. So, let us find out the virtual work. So, one more thing you have to appreciate here, that the degree of freedom is 1 and the generalized coordinate is theta. So, now let us look at the virtual work. Because of this force P, let us say this is x, because of this force P, this bar is going to displace by a length dx. Therefore, virtual work du will be P dx because of that force P. Now, because of the mass, you can also see here that let us say this height is h, because of the mass these bars are going to come close, therefore, their center of mass is going to lower down, let us say by a height dh. So, earlier the center of mass was here, now it will shift to that point and let us say this is dh. So, therefore, because of the mass the virtual work will be, so there are mg plus mg 2 mg into the virtual displacement which is dh, so delta h, and as per the principle of virtual work this should be equal to 0. Let us call this equation number 1. Okay. Note that our generalized coordinates were theta, therefore, this equation number 1 which is right now in dx and delta h has to be converted to d theta. So, let us find the relation between dx and theta or x and theta. So, from the geometry you can see that because this length is L, therefore, this length will be, so x by 2 will be L sin theta by 2 or x will be 2L sin theta by 2. Therefore, dx will be L cos theta by 2 delta theta. Okay. So, we got this dx in terms of d theta. Now, let us look at the relation between dh and theta. Okay. So, again you can see here that 2h will be L cos theta by 2, therefore, dh will be minus L by 4 sin theta by 2 delta theta. Let us put this in equation number 1. So, we have P L cos theta by 2 delta theta minus 2 mg L by 4 sin theta by 2 delta theta equal to 0, and this gives us P cos theta by 2 equal to mg by 2 sin theta by 2 or tan theta by 2 equal to 2p over mg, and from here you can say that theta by 2 is nothing but tan inverse 2p over mg. Okay. Now, let us look at another question. So, this is question number 2, let us say, and the problem statement is following. The mass m is brought to an equilibrium position by the application of the couple M to the end of one of the two parallel links which are hinged as shown. The link have negligible mass, and in the question it is asked you to determine the expression for equilibrium angle theta which is assumed by the links with the vertical for a given value of the moment m. So, again because it has a weight mg, so therefore, this direction is let us say plus y and the moment is applied in that direction. So, let me take the positive moment in that direction. So, therefore, this will be our sign convention. So, let me first make the diagram once again. So, we have these bars here and with this we have 2 bar that is connected, and from here we have the mass m, and of course, it is going to act at g. So, first of all, what will happen because of the moment? So, we can assume infinitesimal virtual displacement because of this m. So, you can think of because of this m, this mass is going to go up. So, earlier let us say it is here and the g is going to go there, and let us say this is delta h. And because of the mass m, you can assume the infinitesimal virtual displacement to go down. So, because of that you can think of that this is going to go down. So, this angle is given theta, this angle is also theta. So, first of all, the degree of freedom is 1, generalized coordinate is theta here, because with this theta I can find out the position of the bar. Now, let us write down the equation of virtual work. Okay. So, virtual work equation is du equal to m is the moment and the virtual displacement which is d theta plus it has a mass mg, and because of this mass the virtual displacement is dh. Now, let me write down this theta and dh in terms of theta. So, this d theta is already in terms of theta. The only thing that I have to do is I have to write down this dh in terms of theta, because theta is our generalized coordinate. So, for that I have to find out a relation between h and theta. So, you can clearly see here that if this height is h, then h is b cos theta, therefore, dh will be minus b sin theta d theta. Let us put that in equation number 1. So, we get du equal to m delta theta minus mg b sin theta delta theta, and this has to be equal to 0. Therefore, m is mgb sin theta or theta equal to sin inverse m over mgb. This is the condition for the equilibrium. That means, to maintain this at an angle theta, you have to apply a moment m, and the relation is this. Now, let us look at one more very important problem on this concept. So, let me again write down the problem statement, and it is following: using the method of virtual work, determine the couple m required to maintain equilibrium of the mechanism shown. So, you can see here that the degree of freedom is 1 and the generalized coordinate is theta, because with this 1 theta I can find out the position of the link. Now, again the sign convention, the force P is applied in that direction. So, let me take this as positive x, and the moment is applied in that direction. So, let me take this direction as positive direction. Now, let me draw the system. So, we have a pin joint here, and then here we have some kind of slot, and we have the link like this, and you apply a force P, this angle is given that it is theta, and the moment m is applied to keep this thing in equilibrium. Now, because of this force P, we can assume that the displacement is going to be like this. Okay. Let us say this distance is x and this is dx. It is already given that the length of each link is L. So, therefore, this is L, this is L, that is also L. And now, we are in a position to write down the equation for virtual work. So, the virtual work equation is delta u equal to 0. In this case, we have m delta theta because of the moment, and then we have p, and the virtual displacement is delta x equal to 0. Now, again because our generalized coordinate is theta, therefore, we have to write down this equation only in terms of theta. So, this is already in delta theta, we have to write down this dx in terms of d theta. For that, we have to find out the relation between x and theta. So, you can see here that x is 3L cos theta, because this length is L, this is also L, and this is also L. So, the x will be 3L cos theta. From here we can find out that dx will be minus 3l sin theta delta theta. So, this gives me the relation between x and d theta, and let us put that in equation number 1. So, we get m delta theta minus p into 3l sin theta delta theta equal to 0, and this gives me the relation between m and p. So, m equal to 3 p l sin theta. So, that means if I want to maintain a angle theta and on this system a force P is applied, in that case I have to apply that much moment at point E. Now, let us look at the generalization of this example, and here the problem statement is following. The folding linkage is composed of n identical sections, each of which consists of two identical bars of mass m each. Determine the horizontal force P necessary to maintain equilibrium in an arbitrary position characterized by the angle theta, and it is also asked that does P depends on the number of sections present. So, again here the degree of freedom is 1 and theta is the generalized coordinate. And let me draw the schematic once again. And here you are applying a force P, this angle is given as theta. Okay. Now, since these links has a mass m, therefore, the mass of this part will be 2 m and the weight will be 2 mg. Similarly, this will also be 2 mg and that will also be 2 mg. Now, because the force P is acting in this direction, so let me take this as positive x, and the force mg is acting in that direction. So, therefore, let me take positive y in this direction. Now, let us write down the equation of virtual work. So, we have du equal to, so let us say this whole length is x. So, it will be p dx, wherein we assume a virtual displacement of delta x because of this force P. So, let me just show you once again. So, this part is dx. So, du will be p dx plus, because of this force. So, there are 2 mg force, but there are n such sections. So, therefore, the total weight will be 2 mg into n, and because of that its center of mass is going to lift. So, let us say this is y, and because of this mg force we can assume the virtual displacement to be like that, and therefore, its center of mass is going to come down. So, it will be 2 mg n into delta y equal to 0. This is the virtual work equation. Now, again we have to write down this delta x and delta y in terms of theta, okay, because theta is the generalized coordinate. So, let us first see what is x. X is n, because there are n bar, into 2b sin theta by 2, because this length is given that it is b. So, this part is b, this is also b. So, for 1b the projection in the x direction will be b sin theta by 2. Therefore, for the n such bars the total x will be n into 2b sin theta by 2. Similarly, you can see here that y will be b cos theta by 2, and this equation helps us to write down dx in terms of d theta. So, from here I can see that delta x is 2 n b by 2 cos theta by 2 delta theta, and this gives me delta y equal to minus b by 2 sin theta by 2 d theta. Let us put that in equation number 1. So, we get p into n b cos theta by 2 delta theta minus 2 n mg b by 2 sin theta by 2 delta theta equal to 0. So, 2 will get cancelled here, and we get p equal to mg tan theta by 2, and from here you can also see that it is independent of n. So, p does not depend on n. Now, let us look at another question, and here the problem statement is following: with W1 W2 are fastened to a light inextensible string ABC at the points BC, and the end A is fixed. At C, a horizontal force P is applied, and AB, BC are inclined at angle theta and phi to the vertical. Then for equilibrium, prove that P is equal to W1 plus W2 tan theta, which will be equal to W2 tan phi. So, we can think because of the weights W, it is going to move like this, and because of the force P, we can think that the system is going to move like that. Now, you can also appreciate that here the degree of freedom is 2 and theta and phi are the generalized coordinate. Now, let us write down the virtual work equation, which is delta u equal to 0. Let us say this length is x, then because of this force P, it is going to move in the x direction. So, therefore, the virtual displacement is dx. Now, let us say this height is y1 and this height is y2. Therefore, du will be p dx plus, because of w1, let us say the virtual displacement is dy1, and because of w2 the virtual displacement is dy2, and this has to be equal to 0. Let us call it equation number 1. Now, again note that this dx, dy1 and dy2 we have to write down in terms of the generalized coordinate. So, therefore, in terms of theta and phi. Now, from the geometry you can see that x is equal to a sin theta plus b sin phi, and y1 is a cos theta and y2 is a cos theta plus b cos phi. Therefore, I can find out what is delta x. Delta x will be a cos theta delta theta plus b cos phi delta phi. Similarly, delta y1 will be minus a sin theta delta theta, and delta y2 will be minus a sin theta delta theta minus b sin phi delta phi. Let us put these values of delta x, delta y1, delta y2 in equation number 1. So, we have p into a cos theta delta theta plus b cos phi delta phi minus w1 a sin theta delta theta minus w2 a sin theta delta theta plus b sin phi delta phi equal to 0. Let us collect the coefficient of delta theta and delta phi. So, we have delta theta P a cos theta minus w1 a sin theta minus w2 a sin theta plus delta phi P b cos phi minus w2 b sin phi equal to 0, and for this to be 0, both the coefficient of delta theta and delta phi has to be 0. So, let us first see this. So, we have P a cos theta equal to a sin theta w1 plus w2, and this gives you P equal to w1 plus w2 tan theta. This is something that was asked in the question statement. Now, let us look at this equation. So, this gives you P b cos phi equal to w2 b sin phi, and this gives you P equal to w2 tan phi. This was also something that was asked in the question. So, with this, let me stop here. See you in the next class. Thank you.